This video is part of the series on the Control101 MATLAB toolbox. Here we're going to look at open loop behaviours. The community then agreed on an outline structure for a Control101 course, and the MATLAB Control101 toolbox has been developed to support such a course. The reason being that MATLAB tools enable visualization and support tedious number crunching so students can focus on concepts. This video focuses on the apps designed to support the understanding of behaviours of linear systems and how those depend upon pole positions. Let's have some context then. We're going to take a simple transfer function model like the one shown here, y of s equals g of s, u of s, where y is the output and u is the input. We're interested in how the behaviour of the output depends upon the model, and notice we're not interested in behaviours linked to the input signal u of s, so we're going to assume that u is a step for convenience. System poles then. A transfer function has poles, and you can find these if you do a partial fraction expansion. For example, like the one here, g of s is a over s plus a plus b over s plus b, and so on. In general, system behaviour is linked to these system poles because you can find basically a link between a factor a over s plus a and the time domain behaviour capital A e to the minus a t. We're not going to dwell more on that because that's something you should see in the manual and in your notes on transfer functions and inverse Laplace. You may also notice that you will see pictures like this where the behaviours are linked to pole positions. So poles that are in the have a non-zero imaginary part are oscillatory, and a large imaginary part, they may be too oscillatory. So the purpose of this app is to help students reinforce understanding of these behaviours. So it allows them to enter a variety of systems of different orders, stable or unstable, oscillatory or not, and explore the associated open loop behaviour. You can also move poles and zeros directly by dragging their positions in the bottom right hand plot. Again, look at the manual if you want more detail, and this will open automatically when you run the file. So let's do a live demonstration. Here's the app here, and you can see at the moment we've got a default plant which is first order, and there's the response. I've got other options, a default second order plant, a default underdamped plant, and a default high order plant. So you can play around with those options. You can have random choice if you want. So with a random choice, you can choose do I want real poles or complex poles. You can choose to be stable or unstable. You can choose to be low order or high order. So basically, you can create new random examples under the specification that you have set. And this allows students to explore relatively efficiently how behaviour changes as pole changes. Now, the key point here, perhaps if I do a new random example, is that you can move these poles. At the moment, I've got poles at -10 and -7. So I can move that pole. See, I drag it with the mouse, and I can see how the behaviour changes. I can change that pole. And I can see how the behaviour changes. Let's do a new random example. These are now complex. What if I reduce the complex part? Okay, so you see I've dragged those down and made them not so large in the imaginary side. So it's not quite so underdamped, but hopefully you get the point. You can change these if you want and see how the behaviour changes. Now, there is also an option custom where you can enter your parameters directly. So there, I've entered them directly. And so if students have got specific examples they want to explore, they can do that. And you'll see in the bottom left, it says these are your current poles, these are your current zeros, and that's your current transfer function. So conclusions. We've demonstrated how to run and use the behaviour app in the Control101 toolbox, and you can deploy this in lectures if you want, or student private study, to help students appreciate and relate their technical and analytical learning. And the manuals contain some MATLAB source code and can be used as templates for individual investigations.